Welcome to A-Level Chemistry Lessons. In this video, we are looking at enthalpies of solution and hydration. By the end of this lesson, you will be able to define and use the term enthalpy change with reference to hydration and solution. You will be able to explain in qualitative terms the effect of ionic charge and of ionic radius on the numerical magnitude of an enthalpy change of hydration. You will also be able to construct and use an energy cycle involving enthalpy change of solution, lattice energy, and enthalpy change of hydration. Finally, you will be able to carry out calculations involving the energy cycles. In our introduction, let us define an infinitely dilute solution. An infinitely dilute solution is one where there is a sufficiently large excess of water that adding any more does not cause any further heat to be absorbed or evolved. Let's look at the scenario here. In this scenario, we have got the water molecules, and then we also have particles of solute A and also C. So in this one, we are calling it an ideal solution because both the solvent and the solute are present. However, continued addition of water will cause all the particles of the solute to disappear. And at that point, that is what we're referring to as an infinitely dilute solution. Standard enthalpy of hydration is the enthalpy change when 1 mole of gaseous ion is dissolved in water at standard conditions to form an infinitely dilute solution. This enthalpy is exothermic. Let me try to put some emphasis. Enthalpy change of hydration is something that we'll be using in our calculations. So let us just emphasize on something. So here we're going to deal with enthalpy of hydration and enthalpy of solution. Now those two are closely related. So as we go through the discussion, I'll be placing much emphasis on the differences between these two. So when you are dealing with the enthalpy of hydration, the energy that is involved is you are adding water to gaseous ions. So when you add water to gaseous ions, they are going to become hydrated ions. Now the energy change that is involved in this conversion here is what we call the hydration energy, or simply the enthalpy of hydration. Please take note, it deals with gaseous ions. Factors affecting the ion hydration energy. The two key factors which affect lattice energy are the charge and radius of the ions that make up the crystalline lattice. For larger ionic radius and smaller ionic charge, there is less exothermic, meaning lattice energy is less. For smaller ionic radius and large ionic charge, there will be more exothermic energy, which means the lattice energy will increase, and so will the enthalpy change of hydration. How does ionic radius affect lattice energy? The lattice energy becomes less exothermic as the ionic radius of the ion increases. This is because the charge on the ion is spread out more over the ion when the ions are larger. The ions are also further apart from each other in the lattice. The attraction between the ions is between the centers of the ions involved. So the bigger the ions, the bigger the distance between the centers of the ions. Therefore, the electrostatic force of attraction between the opposite charged ions in the lattice are weaker. Let's look at this illustration here. We have 3 compounds, 1, 2, and 3. All these 3 compounds, they have sodium cation as a common cation, but the difference comes in their anion. You notice that the size keeps on increasing from chlorine to bromine and finally to iodine. So what is happening here, notice, is as the size of the anions is increasing, the lattice energy is also decreasing. So here, the smaller chlorine and the sodium cation here, this is a positively charged nucleus, and for the chloride here, it's negatively charged. So the electrostatic force of attraction here are a bit closer, so they are going to be tightly held. Therefore, the lattice energy is going to be more exothermic or more negative. When the size increases a little bit, it means the distance between the positive charge and the negative charge here has increased. The increase in the distance here, it means that the electrostatic forces of attraction here, they've weakened a bit compared to scenario number 1. Therefore, the energy here has become less negative compared to scenario 1. Same thing will apply when it goes to the iodide ion, which is even larger than the bromide ion. It means that the distance from this positive to this negative has increased even the more. Therefore, the electrostatic forces of attraction here has even become weaker. Therefore, a drop in lattice energy. In conclusion, we are saying the lattice energies get less exothermic as the ionic radius of the ions increases. Let's look at the effect of ionic charge on lattice energy. The lattice energy gets more exothermic as the ionic charge of the ions increases. The greater the ionic charge, the higher the charge density. This results in stronger electrostatic forces of attraction between the oppositely charged ions in the lattice. As a result, the lattice energy is more exothermic. Let us look at this illustration. We have two compounds, sodium oxide and calcium oxide. The oxide in sodium oxide and the oxide in calcium oxide are the same. The difference will come in from their cations. Sodium has a charge of 1. Calcium has a charge of 2. So since the charge of calcium is more than the charge on sodium, it is expected that lattice enthalpy will be more because there will be stronger electrostatic forces of attraction between the calcium and the oxygen compared to the sodium and the oxygen. Therefore, as the ionic charge increases, the attraction between the ion increases and lattice energy also becomes more negative, which also affects the melting point, which increases. Let's look at the enthalpy of solution. The enthalpy change of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to give an infinitely dilute solution. Again, I'll go back to my emphasis on the difference between the enthalpy of hydration and the enthalpy of solution. For the enthalpy of hydration, we are adding water to the ionic substance. But for the enthalpy of hydration, we are adding water to the ions. That is the difference. Please take note of that one. The symbol AQ is used to show that the solid is dissolved in sufficient water. For example, the enthalpy change of solution for potassium chloride are described by the following equation. Number 1, it can either be shown like this. KCl as a solid, you add AQ, which is water, and then you just change the state from solid to AQ, or you show the dissociated form where KCl solid, you add water, and then you're going to say K plus AQ and then Cl minus AQ. So this is the dissociated form. Either way is accepted, provided you know what you are doing. So enthalpies of solution may either be positive or negative. In other words, some ionic substances dissolve endothermally while others dissolve exothermally. The process of forming a solution. The process of forming a solution or of dissolving a solution is often referred to as the dissolution process. In the dissolution process, the solid must separate into ions and become dispersed with the solvent molecules between the ions. The overall process of dissolving a solid can be treated as an energy cycle. Let's look at some illustration here. So here you can look at the starting point here we have is the ionic lattice, which is probably a solid. When you break this one apart into its gaseous ions, that will become reverse lattice energy. So which means the symbol, if we are moving from the solid to the gaseous ion here, we expect the lattice energy to be positive. However, in all calculations, lattice energy is considered to be negative. From these gaseous ions here, if we add water to become hydrated ions, then we are dealing with the enthalpy of hydration. If from the solid here we added water, then we are going to have an enthalpy of solution. This understanding is going to be very important in our calculations. The cycle relating solution enthalpy, hydration enthalpy, and lattice energy using sodium chloride as an example. This one here, we will safely call it an energy level diagram. Please take note, this is an energy level diagram. So again, we are starting on the sodium chloride as a solid. So if we break this apart into the gaseous ions, then we are dealing with the lattice energy. If we added water to these guys to come up with what is at the bottom here, then we are dealing with hydration energy or enthalpy of hydration. Then here, if we added water, we follow the red arrow here, we are dealing with the enthalpy of solution. So this one, we call it an energy level diagram, which can easily be converted into an energy cycle, as you will see shortly. So the enthalpy of solution is equal to the enthalpy of hydration minus the lattice energy. Please take note of this one. Now, why are we saying the enthalpy of solution is equal to the enthalpy of hydration minus the lattice energy? Look at the arrows here, the way they are facing. Lattice energy and hydration energy, they are in opposite directions. So meaning this lattice energy and the hydration energy, somehow they have to give us the relationship between the lattice energy and the hydration energy. They have to give us the enthalpy of solution. So because these two, their arrows are facing in different direction, that's why we are having a negative, a minus sign here. So in conclusion, we will come up with a formula that will be used in our calculation as enthalpy of solution will be given by enthalpy of hydration minus the lattice energy. So the enthalpy of lattice energy, or just lattice energy. So this is how our formulas will be used in our calculations. But before then, let us see how we can convert an energy level diagram to the energy cycle. So energy level diagram to an energy cycle. So in this case, we are trying to deal with the energy cycle for sodium chloride. Now, the starting point will be the compound that you've been given, the ionic compound you've been given. So what you do is, this one, it needs two things can happen to this one, okay? It's either, because this one is a solid, so two things can happen. Every time you are dealing with this cycle, remember to put three things. So 3 boxes, you can put a box here, a box there, and then you can put a box here, just like the way we dealt with the Hesse cycles at the first year of A level. So here, we are going to put the sodium chloride. Now, if we add water to the sodium chloride solid, then that will be an enthalpy change of solution. So this will give you that arrow there, okay? Enthalpy change of solution. Then you write, you can write your ions in here, because you can write Na plus AQ and then also Cl minus AQ. Now, if you decide that you just want to break these apart, meaning you're going to have Na plus as a gas and also Cl minus as a gas. So these are gaseous ions. Then you factored in. There we have the lattice energy. There we have the enthalpy of solution. Then there we have the enthalpy of what? Hydration. Let us look at clearly what I've just talked about in a more reasonable diagram. So this one will be like this. I said you first write the ionic solid you have. If you add water, this is what you're going to come up with, and then it comes enthalpy change of solution. Then from this one again, if you add water, no, you are not adding water, you are just breaking these apart into the gaseous form, then that will be the lattice energy here. Then if you added water to this one now, you add water to this one. So you add water, which is H2O. Then this will change from gas to AQ here. And that is the enthalpy change of hydration. After doing that, then you can apply your formula which says enthalpy change of solution is equals to enthalpy change of hydration minus enthalpy change of lattice energy. As you can see, the arrows are facing in different directions. So you just subtract this minus that one. And that is your general equation that will be useful in calculations. Points to remember before we can do the actual calculations. Number one, lattice energy is the enthalpy change when one mole of an ionic compound is formed from its gaseous ions under standard conditions. Now, this definition is the one that we use in performing calculations. Therefore, if we move with this definition, we are saying that lattice energy is always exothermic, which means it will always be negative, regardless of how it has been given to you. Because in the previous video, we looked at two definitions of lattice energy, where we said there is a point where if you are if you are breaking apart, okay, if you are breaking apart the ionic solid into its C component ions, then energy is doing what? You need energy to break that one, so it will be endothermic. So at that particular point, lattice energy is positive, and that one we call it the reverse lattice energy. However, the one that is going to be used in the calculation is the one that has been emphasized here. The lattice energy is always what? Exothermic. Therefore, it will carry a negative charge. Another point I want to emphasize on is on the enthalpy change of solution and the enthalpy change of hydration, because these are the three things that you're going to need in the calculations. And if you can easily identify them, then it will be better for you. So, enthalpy change of solution. These two involve addition of water. The difference comes in is for the solution, the water is added to the ionic solid. But for the enthalpy change of hydration, the water is added to the gaseous ion. Please take note. In solution, we add to the ionic solid. In hydration, we add to the gaseous ion. Let's go straight into the examples. So example one, we are saying the hydration enthalpies for calcium chloride ions are given by the equation. Calculate the enthalpy change of solution. So now, here they've given us calcium 2 plus, they are adding water, and it gives us this aqueous solution. So this hydration that we've been given here is just for what? For calcium. Then also chloride, adding water is giving us this solution here. So this one we've been given here is just for the chloride. That's all. Now, in order to solve this one is an example. So they also gave us the enthalpy cycle like this so that we can get any other information that we need. Now, remember, here we are saying in order for us to find the enthalpy change of solution, we need to find the enthalpy change of hydration. So enthalpy change of hydration, okay, then minus the lattice energy, okay, minus the lattice energy. Now, if you look at this cycle here, lattice energy, we know that is where you add your gaseous ions, you add them to give you the ionic solid. So this change, now in this diagram, what we've been given is the reverse lattice energy. So meaning in our calculation, as we plug in this value of lattice energy, it is going to have a negative, okay? It is going to have a negative because the standard lattice energy that we are supposed to use in calculations is the one that comes from the gaseous ions to the ionic solid, not the other way around. So if they give you the positive value, just know that it's for the other way around, and that positive value cannot be used in the calculations. Please take note of that one. So we have our lattice energy. But how about our hydration energy? Because according to our formula, we need the total hydration energy and the lattice energy as well. So the total hydration energy here, we need to add the hydration energy of calcium and also the hydration energy of chloride. But when you look at your cycle here, the cycle should be composed of balanced chemical equations. Please take note, the cycle should be made up of the balanced chemical equations. So checking from the balanced chemical equations, you can see that where there is Cl here and where there is Cl, there's a 2 in front. So we have to multiply this value by 2. We have to multiply this value by 2, then the answer we add to this one, and that will be the hydration. And then we plug into the formula. I hope that explanation is making sense. So here, remember, enthalpy of solution is equals to enthalpy of hydration. So by our calculations here, if you add, you multiply this one by 2, this one here, if you multiply it by 2, you should be able to get minus 728, okay? And then you add this value 1650 here so that you can get your minus 23, okay, minus 2378. Okay, it's just a matter of substituting in here. Then the lattice energy, you know that it's the minus, also it's 1650. So if you compute this one, you discover that the minus which is here and this minus will give you a positive. Okay, will give you a positive, or you will give you a positive. The answer you are going to get is the same as when you follow this route which has been used here. So what has happened here is very simple. This lattice energy here, that is the one that is here, then the hydration energy, this hydration energy was just put on the other side, which is not a big deal. So this and that is what was giving us what? The minus 23 something. So the minus and the minus gave us a positive when you plug into this one, and then you eventually come up with the negative 120 kilojoules per mole. So that was the first example. This one was meant to just explain the basic principles. But let's do 2 more examples on this one and see how far it will take us. Okay, so this one is supposed to be example number 2. So example number 2. So the lattice energy of sodium chloride is plus 788 kilojoules per mole. The estimated enthalpies of hydration for sodium and chloride ions are negative 406 kilojoules and negative 363 kilojoules. Estimate the enthalpy of solvation. So solvation is the process of forming a solution. So what they are looking for is the enthalpy change of what? Of solution. So the first thing that you're going to do is also you're going to come up with the energy cycle. So remember, we've already done the one for sodium chloride. So you just add water directly to this solid, you come up with the enthalpy of solution. Okay, you break it apart, you come up with the lattice energy. The lattice energy, because the sodium plus and Cl minus will be in their gaseous phase. Then you add water to their gaseous phase, you know, the same things that we talked about. So it will look exactly like this. So this is what I was talking about. You add water to here, directly water to this one, you can come up with this one. So it will be a solution. Then you break it apart, you come up with the lattice energy because they are in their gaseous phase. Then you add water to this one. So you add water, which is H2O. Then this you convert from G to AQ. So that is hydration. After which, we can find, because remember our formula needs us to have the total hydration. So you add this plus that, and it gives you that one. Then you plug into the formula here, which says enthalpy change of solution is equals to enthalpy change of hydration minus the lattice energy. So you just plug into those values and you come up with your positive 19 kilojoules per mole. Example number 3. Example number 3. This one says the enthalpy change. So the enthalpy change, so please take note that in the previous example, the enthalpy, the lattice energy was given to us was positive. But I did make mention that never should you use lattice energy in its positive form. You need to assume it's negative. That is the only way you can use it into calculations. So here, they've given us the enthalpy the enthalpy of crystallization for KCl is this one. Okay, so they've given us crystallization, process of forming crystals, which is an ionic solid. So they've already told us that it's negative. The enthalpies change of hydration for potassium and chloride are this value and that value. So from these values, estimate the enthalpy of solution for KCl. So again, the same processes and the cycle will look like this. Okay, so you create your cycle like that. But even if you don't do your cycle in case of the exam, you can just go straight and substitute into the formula because you already know it. So of course, if the hydrations were given to you individually, you add them together. So you add this and that to give you that total. But remember, as you are doing your additions, you consider the stoichiometrical coefficients. But in this case, the stoichiometrical coefficients are ones, so we just have to ignore them anyway because one cannot change anything. So you find your total and then you already have your lattice energy. So the only thing is you plug into this formula and you get your answer as 30 kilojoules per mole. All right, so that is just an emphasis on the energy level diagram, which we have already discussed. Okay, let's look at example number 4. Example number 4 says calculate the enthalpy of hydration of the chloride ion in potassium chloride. So potassium chloride, we know it's KCl. So what they want is for us just to find the what for the Cl, meaning the K they've already given us using the following data. So the lattice energy for KCl they've given us is that one. Then the enthalpy change of solution they've given us is this one. So this is for KCl. Then they've given us the hydration energy for just the K. So this is the one you're going to use here. So the first thing that you're going to do here, you find you write a formula for the hydration. So the overall hydration for KCl will be given by, so here the overall equation will be given like that. That is after you make hydration the subject of the formula. From the general equation we've been using, this is what you come up with. Now we know that on the part for hydration here, this can be broken into two parts. The overall hydration will be given by the hydration of K plus the hydration of Cl. And then you just substitute into this one. Now the lattice energy they've given you, which is -711 kilojoules per mole. Then the solution they've given you is 26 kilojoules per mole. Then also for K they've given you is -322 kilojoules per mole. So you just substitute it there, you substitute. So the only thing that will remain X is this one here. And then you solve the equation. After solving the equation, you are going to find the answer to be -363 kilojoules per mole. Let's look at example number 5, which is a little bit different from what we've been dealing with. So this one says, using silver sulfate as an example, complete the following Hess's law energy cycle relating the lattice energy, the enthalpy change of solution, and the enthalpy change of what? Hydration. On your diagram, include the relevant species in the two empty boxes. Label each enthalpy change with its corresponding what? Symbol. Complete the remaining two arrows. That's very important. So here we are. This is what we are supposed to do. So again, look at this one. This is the ionic solid. That's where you start from. So the ionic solid can only be formed from its gaseous what? Its gaseous ions. So the gaseous ions of this guy, we expect that we're going to have Ag, okay, which is a metal, so it's going to be plus, and it will be in its gaseous form. Then we have the sulfate here, which is SO4, okay, SO4, 2 minus, and this one also is in its gaseous form. So if that be the case, then this one they've even given us the arrow. So meaning what we expect to be here is actually the lattice energy, okay, the lattice energy, because, and this one is a negative value because it comes from the gaseous ions into the ionic solid. So the first here we expect to have the lattice energy, and this one will come from where? These guys here, and make sure it is balancing, okay? So silver just has a valence of 1. And when you look at this 2 that is here, it jumps to the front here. I think you still remember your IGCSE. Okay? And then, since we have this one now, what next? The next thing is we can add water here. Okay, we can add water there. Okay, we can add water there. Since we are adding water to the ions, we expect that we're going to have some hydration here. Okay, we're going to have the enthalpy of hydration. So meaning this arrow is actually supposed to be like that. Then also from here, we can also add water to this one so that the arrow comes here. And then we have what? The solution now. So when we add water to these ones, they will just change into aqueous. Okay, and then we add water to this one will also change into aqueous. So from the solid here, it will change into aqueous, or you can also write it in the dissociated form. So this is how you can fill up this one. If you just understand the definition of this one, the definition of that one, and the definition of that one, you can solve any question on this topic. Energy level diagram versus the energy cycle. Just in conclusion, you saw how we are able to convert from this one into this one, or from that one into that one. Please take note, the starting point in most cases is the solid itself. Okay, the solid itself. So the solid itself, you add some water there so that you can have some solution, and then or it can give you these ions here. And then the gaseous ions here also, as you can see the arrow coming down, it is coming here. So please just take a pause. This slide was put for you to just analyze and see the relationship based on what has been discussed. All right, thank you so much for visiting the Eagles Edu Concepts YouTube channel. Please remember to subscribe and click on the bell notification so that every time content is posted, you'll be notified. Thank you so much. See you next time.